Hey folks, welcome to this episode on collision theory. So, what is a collision? Why is it important? Well, for a reaction to occur between particles, they first must collide, and they must do so effectively. Without an effective collision, there's not going to be a change from reactant into product. Now, what is an effective collision? Well, that's explained by something called the collision theory, and it's a proposed method and specification of what has to happen between these particles for there to be an actual reaction, aka turning a reactant or sets of reactants into products. So, for an effective collision, there have to be a few things that have to happen in order for this to happen. The particles, they could be atoms, ions, radicals, molecules, whatever, they have to come into physical contact, so aka they have to collide with one another. Now, once they do, two other things have to take place. They have to collide in the correct orientation so that they hit at a specific part. So one part of the molecule has to hit another specific part of the other molecule. So that's the correct orientation. And the other thing is that they have to hit with enough kinetic energy to overcome something called the activation energy, and that's the minimum amount of energy required for the reaction to take place. So when it looks like this, we have our two reactants. We have NO3 and CO. In this case, they're moving kind of slowly. It's shown by the one little hash mark over here. They are in the correct orientation. The carbon is going to hit this nitrogen over here, but they're reacting a little bit too slow. They don't have enough kinetic energy to overcome the activation energy, and we'll talk more about what that is in a second. But they simply just bounce off. There's no reaction. They keep existing as they were, and that's it. In this case, we have a lot of kinetic energy shown here and here, but you can see that they're not orientated in the right way. So the oxygen hits the nitrogen, whereas the carbon is the one that needs to hit the nitrogen. So again, because they're not in the correct orientation, they simply bounce off and there's no reaction. If we play our cards right, and we have this, they're both moving in the right kinetic energy, and they're both oriented in the correct way. As they hit, this carbon will hit this nitrogen, bonds will break, new bonds will form, and will create new reactants, aka we've just had a chemical reaction. So what does it mean by correct orientation? Well, they have to hit in the proper geometry. Now this depends on the reactants. Different reactants means different requirements. And here we have ethane, or ethene, ethene, because we have a double bond, or acetylene, as you used to call it. And here we have hydrogen chloride, for example. We have a hydrogen, we have chlorine. Now, for this reaction to happen, this hydrogen has to approach this double bond. Now, once again, it has to hit in this correct orientation and with enough energy to overcome the activation energy. But this is the orientation that it requires. If you had this orientation, no go. This orientation, no go. This orientation, no go. You have to hit this double bond, and you have to hit it with the hydrogen. Now, when we look at this, why is this the reason? Well, the chlorine in this case is very electronegative. It's very negative, and so if it tries to hit this double bond, which is a high electron density of electrons, okay, we have our sigma bond, and we have our pi bond. There's a high density of these electrons. So something that's very electronegative, high density of electrons, they're just going to simply repel each other, and no reaction is going to happen. This is a lot smaller as well, so it can fit in here and break in that double bond. Now, the activation energy is the minimum amount of energy required to overcome this activation energy, or the energy required to start this reaction. If you don't have it, you have no reaction. So you have to hit in such a way for number one, hit with the right orientation, but also overcome this activation energy. So in this case, this kind of gives us a potential energy diagram of what we would see from enthalpy. Now, in enthalpy, when we were looking at, this is an exothermic reaction. Reason being is that the potential energy of our reactants is a lot more than the potential energy of our products. So when we were looking at enthalpy, this reaction would look like this. Here we have our reactants, here we have our products, and the delta H for this reaction is going to be negative. Okay, so we release energy to the surroundings. But what thermochemistry didn't say was that in order for this reaction to happen, for this enthalpy change to actually occur, this reaction requires a little bit of energy to get going. And that energy right here, so right here to right here, is our delta H, which is going to be negative. But from here to here, for this reaction to actually happen, this is our activation energy in the forward direction. Okay, forward meaning that we're going from left to right, reactants to products. So again, this reaction, if we can't possess this amount of activation energy through the collisions, we won't be able to have this reaction actually occur, and therefore there won't be any enthalpy change. If you think about it, if you go back to something common like lighting a barbecue lighter, you have butane and you have oxygen, which are both very, very, very unstable compounds. They both want to react, and when they do, the reaction is explosive. They release a lot of energy into the surroundings. But you have these both things. You have oxygen in the air, and you have butane in a lighter, but there's no reaction. Why not? Why don't they just spontaneously react with one another? Now, when they do react, it is a spontaneous reaction based on Gibbs free energy, but they need a little bit of a spark. They need that little bit to overcome the activation energy. And the thing that allows us to start this reaction is that spark from the flint. So when you spark it, that spark provides enough activation energy for the reaction to happen, and then the enthalpy change that's caused from the burning of butane with oxygen, well, the enthalpy change is going to be negative. That energy is then used to fuel the next reaction to allow it to overcome the activation energy. So once you spark it once, you just have to hold on to that little button to allow the gas to be fed, and the enthalpy change, the amount of heat that's being released, is just going to be fueling the next reaction, allowing it to overcome the activation energy, and etc., etc., etc. So even though we consider that a spontaneous reaction, it does sometimes need a little bit of help to overcome the activation energy, and then will progress normally. So when we look at the activation energy, we have to look at the distribution of particles that contain enough energy to overcome the activation energy. So this activation really plays a key role in determining whether or not a reaction will happen. Now, in any proportion of molecules, if we have a box with, say, we have a box full of oxygen, the particles that are inside this box will not all have the same amount of kinetic energy. Some will have more, some will have less. And this distribution of the number of particles that have a certain amount of energy versus their ability to provide an effective collision is called the Maxwell-Boltzmann distribution. So this is our enthalpy change. Here we see that again, this is delta H is going to be negative, this activation energy. In this box of particles, some of these particles will have enough energy to overcome the potential energy required for this reaction. Some of them will only be able to get up to here. Some of them will only be able to get up to here. The distribution of particles that have enough energy to overcome the activation energy, again, is the Maxwell-Boltzmann distribution. So this is what the distribution looks like. As you can see here, we have this curve. Now the area under the curve shows us the number of particles, and so that doesn't change. This just shows us how many particles have a certain amount of energy. So you can see that the distribution is more so favored to the left. Again, this bottom axis shows us the number of energy that they possess, kinetic energy. So you can see here that a small number of particles have a very small amount of energy. There's a lot of them that have a medium amount of energy, and then there's only a very few that have a very, very, very high energy. Now, in order for a reaction to happen, it has to overcome the activation energy. The activation energy is set for each type of reaction. So different reactions will have different amounts of activation energy. And in this graphic, what we can see is this is the threshold for this reaction to happen. This is the activation energy. So these particles have to overcome this activation energy in order for the reaction to happen. Now, the only particles that can do that are the ones that are found on this side of this distribution. All of these particles don't have enough kinetic energy to overcome the activation energy and therefore cause a reaction to happen. Okay. So in any given sample, we will have a distribution that will be similar to this. Some of them will just have enough energy to move around. Remember that the kinetic energy is translational, vibrational, and rotational. So some of them will only have enough energy to kind of move around, bounce off, but they won't have enough energy to actually cause this reaction to happen. It's only these ones over here that will be able to cause that reaction to actually happen. So if we have the correct orientation and we have enough kinetic energy to overcome the activation energy, what will be produced is something called an activated complex, and this occurs in this state called the transition state. Now, this activated complex is marked by having partial bonds. So some of the bonds here, if we look at our two reactants, there is a bond that's being formed between some of here, but at the same time, we can see that from our products that some bonds will have to be broken. So in this activated complex, you're going to have bonds being broken and bonds being formed. Now, it takes a lot of energy to achieve this transition state. This is a really, really high energy substance. The potential energy of the system increases at this point over here because these reactants must overcome the repulsive forces between the outer electrons of their atoms, and also these atoms have to be separated from one another as the bonds are broken. This requires a lot of energy. So the kinetic energy of these over here have to be on that portion of the Maxwell-Boltzmann distribution that will be able to overcome that potential energy, the repulsive energy, and also the energy required to break these bonds. Now, again, because this is very, very, very high in potential energy, it's very, very unstable. And this transition state, or the activated complex, can actually go back to the reactants if the energy is not there. So sometimes this will proceed to the products, and sometimes it will go back to the reactants, and it depends on the ratio between the translational energy and the vibrational rotational energy of these reactants. If there's not enough translational energy, the velocity of this activated complex will reverse and it will reform the reactants. So overall, all we're trying to say here is that this is a very, very unstable place. It has a lot of potential energy, a lot more potential energy than its reactants, and a lot more potential energy than the products. So it wants to get out of here. It's not going to exist for very, very long. It'll either form your products or form your reactants. But to get there, it requires a certain amount of potential energy, and that comes from the kinetic energy of these original reactants, as shown by the Maxwell-Boltzmann distribution. If this reaction happens, then you get back your activation energy, and if it's an exothermic reaction, you're also going to have a huge enthalpy change in the negative. So that means heat is going to be provided to the surroundings. What's also interesting that, let's say for example we had our products and we wanted to go the back way or reverse, go back into our reactants. For these products to get back into the reactants, first of all, they would have to have enough energy to overcome this enthalpy change. So we lost 226 kilojoules to the surroundings. For this to start happening, we'd have to regain that energy, and obviously this would be an endothermic reaction because we'd have to gain that energy we lost. But not only that, we'd also have to overcome the activation energy from this point to get back to our transition state. Now you can see that the activation energy in the forward direction is 134 kilojoules. It has to absorb that much energy. The activation energy to go from products to reactants is the enthalpy change plus the activation energy in the forward direction. So the total activation energy that these products would have to overcome to get back to this transition state and into reactants is 360 kilojoules. And so this would be a very, very, very slow reaction. It'd be very hard to do. The bigger the activation energy, the slower the reaction. So here we have our exothermic and endothermic, kind of relating this back into thermochemistry. Even though, again, when we're looking at thermochemistry, we had our reactants and our products, and we showed that by delta H being negative. In this case, our reactants and our products were here, and our delta H was positive. But again, as we know, that it's not just the enthalpy change, there's also the activation energy that has to occur. So again, in this case, reactants have a lot more potential energy than your products, but the activated complex that's found in your transition state will have more potential energy than both. As this reaction occurs and your activated complex turns into your products, your activation energy is lost, as well as your enthalpy change over here. Opposite is true here. For reactants to form into products, it has to absorb enough energy to overcome the enthalpy change and also overcome the activation energy. As you form this activated complex, the activation energy is released and you formed your products over here. So once again, as mentioned, the larger the activation energy, the slower the rate of the reaction. So let's take a look at here. We have this reaction, CO2 plus NO2 forms CO2 and NO. Now this is a reversible reaction, as you can see by the double arrows over here, which means that the reaction can proceed in the forward direction or it could proceed in the reverse direction. So our forward direction, I just kind of drew it out here so that you could see what would be actually happening. So our forward direction means left to right. So as you see it over here, but just your one-way arrow there. And the reverse direction would be CO2 plus NO, creating CO and NO2. Now, in this forward direction, our enthalpy change, so the change between our reactants and our products, is negative 226.1 kilojoules. So we lose 226.1 kilojoules to the surroundings as heat. Now, for this reaction to actually happen, we first have to absorb 134 kilojoules, and that's our activation energy in our forward direction. Now, let's say we wanted to go into the reverse direction, turn our products into our reactants. We know that the enthalpy change was 226.1 kilojoules, but what is the activation energy that this has to overcome to do this? So remember that for this reaction, this activation energy in the reverse direction is the summation of the enthalpy change and the activation energy in the forward direction. So what we do is we take 226 plus 134, and the total activation energy that has to be overcome to go into the reverse direction is positive 360.1 kilojoules per mole. So again, this reaction in the reverse direction would be a lot slower than in the forward direction because the amount of energy it has to absorb is a lot more than in the forward direction over here. So if we put it all together here we have bromomethane and a hydroxide ion turning into methanol and the bromide ion. If we have these two reactants over here, BrCH3 and OH, if this collision has the right orientation and the right kinetic energy to overcome the activation energy, what's going to happen is we're going to see that our kinetic energy is going to be turned into potential energy, and that's going to be called our activated complex. So for this to happen, we have to overcome the repulsive forces of these molecules, and we also have to break some bonds. So what we're doing is we're turning that kinetic energy, the rotational, translational, vibrational energy, and we're breaking the bonds, which is increasing our potential energy. Now here in our activated complex, you can see this little dotted lines over here, which means that this Br is actually being displaced by this OH. So this bond is being broken while this bond is being formed. So we're kind of in this limbo. Now as this goes and turns into products, the energy stored in these bonds, the potential energy, is going to be released, and we're going to be releasing them as heat lost, and we'll see that this potential energy is transformed into kinetic energy of our products. Now in this case, this is our activation energy, our forward direction. If we wanted to go back this way, if this was a reversible reaction, we'd have to overcome this activation energy, which is a summation of our forward activation energy and our delta H. Now, because the potential energy of our reactants is greater than the potential energy of our products, this delta H is going to be negative, which means it's exothermic, and we've released heat into our surroundings. So thanks very much for watching. We'll see you next time.